Hi and welcome to another episode of the oscilloscope review that I'm doing. I don't have the oscilloscope right here in front of me, they're up in the lab, but we'll get there in a second. And this is part of a wider series of reviews of different features of these free oscilloscopes. And if you look at one of the other episodes, you can see all the different episodes that are in the planning. Anyway, so about today, what I'm going to talk about, function generators, arbitrary function generators, pattern generators and training signals in these scopes. I'm going to talk about oscilloscopes that are generating signals instead of analyzing signals. And before I go and talk about that, maybe we should first address why you want such functionality in a scope in the first place. Because there are plenty of devices on the market, such as like two Siglent function generator got over here. That might be a better choice to do such things. So let's quickly review what the advantage will be to have such functionalities in an oscilloscope instead of as an external device. Now I think there are a couple of reasons why you would consider to have such a functionality. One of them is Bode plots. All of the free oscilloscopes that we're looking at here can generate Bode plots, and that process is greatly facilitated if there's a function generator built into the scope, even though the Siglent SDS is also able to do it with a specific number of external function generators, and then they're connected via USB connection. Secondly, having a function generator in a scope, an arbitrary function generator, would allow you hopefully to play back signals that were captured by the scope, and I'll later do some experiments with that as well. It can also be very convenient if you would like to do some simple automation type of script. So you would write one piece of script code that actually would do a range of functionalities that you would like to repeat for a number of times. Then having such a thing built into a scope may also offer you some more oscilloscope related training signals that might be very useful. These are training signals that you hardly ever find in external devices like this. So I'm talking about training signals that have got glitches in there, training signals that have particular characteristics, noise, challenges when it comes to triggering them, and so forth. You can get these as separate devices. One example is this REL device I got over here. Let me put it a little bit closer. Yeah, I'll put a separate picture in. This is a specific oscilloscope training board, demo board, that can also generate such signals. But be aware, these are relatively expensive. I think this is about as expensive as one of the signal generators I got over here. Then some of the devices we're going to talk about today do have pattern generators in them, up to 4 different pins. Of course you can have separate devices that do that as well, but that's typically not part of a regular type of function generator. So that can be useful there for protocol generation, if you got more than one pin, for counters, other types of stuff. And of course, having a function generator built into your scope can save you money and perhaps save you bench space if that's important to you. Then again, there's also specific advantages related to having external devices like the ones over here. Typically you get multiple channels. The free oscilloscopes I'm looking at today only have a single channel for function generators. Often they have much more functionalities and settings, so they're going to be much more flexible. They would allow you to externally trigger a signal. They would allow you to externally have a time base, a reference time base for the signals that are generated. You can have multiple devices, for example, synced to the same type source. You could get a very precise type source, like a GPS discipline type of oscillator. You can do all types of things as combining the outputs of these, and well, plenty of flexibility here. And you have a separate device with separate control and a user interface that might be more convenient than having to do it at the same time within your oscilloscope. So there's something to say, I think, for both scenarios. Anyway, today I'm going to talk about 4 topics then, about the regular function generator functionalities. I'm going to talk about the arbitrary waveform generating functionalities. I'm going to talk about pattern generators, and I'm going to talk about training signals coming from the oscilloscopes. And while doing that, I will also do some experiments, and I'll also have developed some specific computer code to generate some signals at various points for today's exercise, and I will also be sharing this code below in the chat. So stay tuned for that. And before we get going, I want to show one little device that I made specifically, basically because of doing this series of reviews. I had a huge mess of all these oscilloscopes, channels being connected to the same source with T-connectors and everything. Some of them were not as reliable as I wanted them to be, so I decided to build a small distribution box that would allow me to connect everything together. I can show, I think, a better picture of it here on the screen. So this is basically just a BNC distribution box. Of course, I had to check whether that works well for the purpose. So I run some tests on my spectrum analyzer, or better on the vector network analysis, and I did a S21 plot. So what we see is that up to 300 megahertz, it's perfectly fine, the splitter. Everything is within 3 decibel of attenuation within that bandwidth. So that's perfectly fine for the type of things that I'm doing here. They're at max a couple of megahertz, so that's good. However, if you would like to use this for higher frequencies, then you should not do it this way. Actually, I also looked it up to 3 gigahertz, and we see it has big issues of attenuation at frequencies higher than the 300 megahertz. The whole reason being that this is not designed at all with RF signals in mind. You really should resort to other types of designs when you're dealing with high frequency signals, and that's not what I did for this particular purpose. But for what I'm going to use it for today and for our episodes, is going to be perfectly fine, I think. Okay, let's quickly move to the lab, and let's go and look at the function generators. So let's start looking at the basic specification of the function generator, and later I'll get to the arbitrary wave generation. So we see here that in terms of resolution and sample rate, both the RTB and the SDS are 14 bits instruments. For the Siglent DSOX, this is not specified. Haven't been able to find it somewhere else, but might be similar. If we look at the sample rate, we see that the RTB uses twice as many samples per second to generate waves than the Siglent. Then if we look at the highest frequency that can be generated in terms of sine signals, that's 25 megahertz for the RTB, but 50 megahertz for the SDS. So the SDS still tries to put out sine waves of twice as high frequency, even though the sample rate is twice as low as the one used by the RTB. That might have some consequences for signal fidelity, but I've not been measuring that. So that was something to be checked if you will be interested in that. Looking further on to functionalities, we see that the RTB and the DSOX offer modulation functionalities, and the RTB also have burst and sweep functionalities. Now, if we compare the specs that we just talked about, and in particular the resolution and the sample rate specs, to a dedicated signal generator, and here I'll be looking at the two signal generator that I showed you earlier in the videos, then the Siglent SDS2000x is actually a 16-bit device with also a considerably higher sample rate at 1.2 gigasamples per second, but it has to be taken into account that is the 4 times interpolation there, and that makes a difference, of course. But it's 16 bits, so you would expect a higher signal fidelity from that. The lower price Siglent SDS1032X that I also showed earlier in the video is 14 bits, so that's more comparable to your oscilloscopes here, and has a 150 megasample per second sample rate. So in that sense, the oscilloscopes are not terribly different from the lower price Siglent signal generator. I mean, if we merely look at things like resolution and sample rate here. Now, turning to the R&B oscilloscope here, let's go and activate the signal generator and see how that is being implemented. So there's a dedicated button to do that. We're into the signal generator. We can activate its output like that, and we see a wide variety of different waveforms. and for many of these waveforms there are quite a couple of options to set various parameters. So if I would go to pulse, I would get duty cycle, edge time. If I go to ramp, I can do polarity and a couple of other things. So you can look at the overview documents which I'm sharing, where you can find all the details about this. But there's a fair amount of flexibility when it comes to settings here. As indicated, there's also a sweep option here. So in terms of sweeping, we can have start frequency, stop frequency, sweep time, and we can also choose whether the sweep is linear, logarithmic, or triangle in shape. So all these type of functions, as you see here, work fairly easy. We got modulation, I'll turn to that in a second. We got burst here, so we can decide how many bursts of a particular waveform we're going to see. And then we're going to get some silence, and we can trigger them again after the silence, or we can have a manual trigger actually coming in from the trigger input of the device. So fairly amount of flexibility here. Here we got the load, which can be specified as 50 ohms and a high load, high Z. All the three devices here have a similar functionality, and it's rather common on signal generators standalone as well. But before you get too excited, this is actually not something about the real output impedance of the signal generator. The signal generator always has an output impedance for 50 ohms, whatever setting you choose here. Changing here this particular thing here, the only thing it does, and you can actually see it happening here, it's changed the values that are shown on the oscilloscope as the output voltages. It halves in two, assuming that the 50 ohm output will be loaded with a 50 ohm load, and that halves the amplitude of the signal. So the only thing it does is just change the numbering and divide it by half. And that's the case here for all the devices. So there's not real different output impedances, but this is just changing the shown value to reflect the load. Now, finally, I will quickly look at modulation here. So we got a variety of modulation parameters: AM, FM, amplitude shift keying, phase shift keying. We can decide how this is being modulated, and then depending on what we choose, we will get parameters. So in the case of FM, we will be getting the frequency and the deviation, of course. So let me activate this here, and what we're actually seeing here is 3 times a second. I can play around with that. Oh, we can put it in rather low settings. Yeah, 1 time a second we'll see the frequency modulation taking place. Now, we'll have to check exactly how this comes out on your monitor, but this is quite well visible. Something rather interesting here, if we look at these waves, and I'm going back to 3 here, is actually how they are displayed by the various oscilloscopes, because that will tell us something about the update rates of the devices. I'm now showing you this FM modulated signal on all 3 devices, and we see huge differences in sense of how they are shown related to the update rate of the devices. And I'm not sure exactly how this is going to come out on the camera, but certainly if you look at the screens yourself, you would see that the Keysight is incredibly fast. It really shows very fast changes in movement of the FM signal. Then comes the Roden and Schwartz, which I think is still okay, but less fast than the Keysight. And I've experimented with this, and I tried to find the best settings to make this show. And the Siglent is not doing that well at all. You can see here that it doesn't update its screen very fast, so we just see discrete captures of waves here instead of what we're seeing here on the Keysight. The Keysight is really incredibly fast, it seems, when it comes to dealing with such fast signal changes. Now we'll look at the Siglent SDS in terms of what it has on offer for waveform generation. So there is a dedicated button to activate it. It lights up if the generator is on, I think. Yes, it does, just like with the Roden and Schwartz. And here we get into the settings menu. So let's take a quick look. In terms of settings, we have a number of different waveforms, a little bit fewer waveforms that we've seen before. And we also got a couple of settings with it, although less settings that we've seen on the Roden and Schwarz. In terms of the frequency of the waveform, like already mentioned, this device offers a higher frequency, at least for sine waves. If I would go to the maximum here, it's not showing you the maximum like Roden and Schwarz does in the menu, but if I type maximum, would see it's 50 megahertz. And if I go back here, 100K, actually I'm back at the same setting as I showed before in the little test with the other devices. When it comes to the amplitude of the output signal, it's actually slightly higher than we've seen on the Roden and Schwarz. This is 6-volt versus 5-volt output setting. And we got a couple of other settings in the menu over here. The output load, as we already discussed it, there's an overload protection and a zero adjust. But other than that, we don't really get any settings here. So this device does not have modulation, it doesn't have sweep, it doesn't have burst, it doesn't have like many of the other parameters that we've seen on the Roden and Schwarz. So this is basically a very basic signal generator that can just output a sine wave or a couple of other shapes, but that's about it. There's no more flexibility available than that from the regular waveform generator. Of course, I'll get back in a minute to the arbitrary waveform part. Now taking a look what the Keysight can do in the respect of waveform generation. So we got a waveform generator which is over here. We get into a menu and we have the rather standard type of options here in terms of shape of the wave. We have the frequency setting and the amplitude setting, and this is a bit of interesting here because this device is more flexible in amplitude than the other devices. We can go here to 5 volts, what we had before, 5 respectively 6 volts were the RGB. I'm just changing here now the channel setting, but actually we can go all the way to 9 volts here, and in some cases even to 12 volts or even 20 volts for square wave. So we have a higher amplitude which is possible, and also kind of interesting in terms of amplitude, if we go here to settings and we go to logic preset, then we can actually define the output, and I think it makes sense if we have like a square wave or a duty cycle type of thing or a pulse, to TTL level, various CMOS levels, and even lower 1.8 volts level. So that's a nice little touch here in terms of in terms of amplitude levels. If we continue here in the settings, one of the interesting things here, we got modulation as well, and here we can choose between AM, FM and FSK. There's no amplitude shift keying, but I still think it's a fair type of offer. We would have the same parameter per type of modulation. So for FM, we would have the frequency and the deviation. Yeah, let's just turn it on and we actually get to see exactly the same picture as we were looking at before. There is one nice little other trick that this device has in its sleeve that I haven't seen in any of the other devices yet, and that is the relationship between the waveform generator and the trigger section. Now we're simply triggering on a positive edge through 0. That's fine because that's the input. But there might be a situation in which you're feeding this signal of the waveform generator to another device, picking it up again and having some trouble triggering to it properly. So what you can do is go to the trigger section, trigger type, and then trigger edge is just a regular type of thing. So the thing I want to show you is not there, but trigger source, actually, you got trigger sources. And here you see we got the waveform generator as well as the modulation frequency, which is now the 3 Hertz of the waveform generator. We get a little bit weird thing, but it doesn't matter. But so you see you can directly trigger on 2 different parameters coming from the waveform generator. And that is kind of a unique thing. I haven't seen that in the other oscilloscopes, and that will be kind of harder as well if you use an external signal generator, unless of course you would run additional cables and you would have like a trigger out coming off your waveform generator, or generate a second waveform on the other channel with exactly the same properties and feed it into the trigger section here. But I think it's a nice little touch here that I have not seen in other devices. Yet the overall implementation of the waveform generator is not as extensive as we've seen on the Roden and Schwartz. We don't have things like burst and sweep and that type of possibilities. Let's first compare some basic specification of the arbitrary waveform generators. So we see that both of the oscilloscopes support 14 bits resolution. The sample rate is much higher for the SDS than for the RTB. I'll say something about that in a second. The waveform memory of the RTB is a generous 32K and 16K still for the SDS. The maximum frequency of the ARP signal is 10 MHz for the RTB and 5 MHz for the SDS. And this is also a bit where my question comes in about the sample rate, because if the sample rate was really as high as 125 as the specifications say, I wouldn't see why the max frequency would be so limited. So I've got some questions here on the specs, but I leave it to others to determine what's actually correct. Now, one of the important things I think of such an arbitrary waveform generator is where you can get the waveform from. And most importantly, whether you can get them from an analog channel, because in my view, that is really the added value of having this in an oscilloscope instead of having it as a separate device. Now, for the RTB, we can indeed get it from an analog channel. We can also get it from a mesh channel or a reference channel, or you can do a regular type of file upload. For the SDS, you can also get it from an analog channel, although I'll talk a little bit about that in a second, because I'm having issues there, don't get that to work. You could also get it from a specific piece of software, EasyWave software, similarly there have an issue, going to talk about that. Then there's the regular file upload, and the SDS is the only one that has a number of presets already available there. And then we see finally in terms of specification that the RTB has also a preview and a cut function for waveforms. Now, how does this compare to a standalone function generator with an ARP functionality? So I'm also showing here the specs for the most expensive signal, Siglent signal generator that I talked about a little bit earlier, the SDG2042. So its resolution is higher. Its sample rate is also higher, although that also depends on the specific mode the device is running in. But interestingly, the waveform memory of the standalone version is only half that of the SDS scope and only 1/4 of the RTB scope. Max frequency is a bit higher at 20 MHz, and the files come either from a file upload, obviously not from an analog channel because it's not an oscilloscope, and it got way more presets. But altogether, I would say that these arbitrary waveform generators as we find in scopes do not compare that badly at all when you compare it to a standalone device. Now let's take a look at how the arbitrary waveform generator is implemented. First the Roden and Schwartz. And what I first want to do is capture a signal from the analog channel and being able to reproduce it, because I think that's one of the most useful things to have such an arbitrary waveform generator into an oscilloscope. So the input signal that you see right now is a signal where every 5 seconds or so a very short burst is coming by. And this burst is actually a double chirp type of signal, and I want to investigate that more closely, make an arbitrary waveform out of it, and then replay it much more frequently than it's currently being replayed. And that way I could use it and test it on a filter and the characteristic of the filter and everything. So now let me first invest this waveform a little bit closer. Let's see if it's only every 5 seconds, so let me see when we get a trigger action. Oh, we got one here. So this is the waveform. I think we can make it slightly bigger. Let's wait for one more trigger. Yeah, there it was. And we can move the signal a little bit here to the left. And let's get one more trigger going. We got trigger waiting. Yeah, the trigger is there. Okay, so we captured this particular waveform now. Okay, now I'm going to the waveform generator. I'm going to choose arbitrary waveform, and from there I can go to the setup menu. And this is basically where I do the copying. I can make the waveform visible, and what I see here is actually a previous waveform that is still there for my earlier exercise, from an earlier exercise. Now, copy source 1, that's the source I want to copy. I click the copy button and I do see a copy having been made. Actually, what I'm going to do is turn channel 1 off. So now we're only seeing the arbitrary waveform generator signal that we got here. If we go back here, we can make it visible and invisible. We also have an option to cut that waveform. So I could basically say that the only parts I'm interested in would be that part here, and wait, I have to use the little scissors here. I'm sitting a little bit in the way of the camera, I'm afraid. Little scissors. Yeah, so that looks like the part that I would like to have here. There's also alternative here. I can set like the full period, set what's seen on the screen, everything in the waveform memory. I don't need anything like that. I think I'm fairly happy with that particular selection that I got right now. So I'm going back here and it should be loaded now. Let me just turn the visibility part off, and now I should be able to activate this on the oscilloscope channel. Now let me go and look at the signal I just created. I have to get the cable out of my auto signal generator and the arbitrary waveform generator. Yeah, we see it coming in. Let's see, let's make it slightly bigger. And there we go. We got a signal that we just generated. I can go back to the signal here and take one more look at it. So this was a signal as we just got it. See it at a slightly different frequency that we loaded into the signal generator. So as we can see here, that works pretty smooth with the RTB. Now we could also generate the same type of signal from a reference channel or from a math channel. I'm not going to do that now. Now I would like to look at loading a signal from a external file that has been prepared in advance. In order to do so, I created a couple of waveforms on my computer. Actually, I wrote a little Excel program for it, and I'll be posting that program in the GitHub and provide a reference to it. So what does this little program do? It actually can create a waveform that is a fundamental wave plus a number of higher harmonics that you can select yourself which harmonics and their relative amplitude. And this program can also create the arbitrary waveform of a desired length. So you can make, like, for example, 8K or 16K or 32K. So for the RTB I'll do 32K. And then the program will calculate all these 32,000 points for the fundamental, but also for each of the harmonics, add them up together, and then also create the particular output file that you need for the device, because all of these devices need their output file in a particular formatting. It's usually a comma separated file, but it needs a little bit of a header and everything. So in the little program that I wrote, you will see both the output file preparation for the RTB and the output file preparation for the SDS being available. So now I already created this waveform in advance. I have saved the comma separated value file on a memory flash drive, which is right now in my device over here, and I'm going to take a quick look at it. So I'm going to go back to the generator. I'm going to go to arbitrary setup. I'm going to load a file on the USB as the location, and there RTB 32K, and this is the file I created for RTB, and it's 32K length, can be selected here, loaded, and there we go. Again, we have it on visible, but it's already shown on channel 1 as well, because I got channel 1 activated. So let's just take a look at channel 1 on the device. Let's put the wave in the middle, and there we actually got our waveform. So this is precisely the waveform as we also saw it in the Excel file. And actually now we're seeing slightly over 1.5 waveform or so. In order to know whether this waveform really does have the higher harmonics that we were thinking about, we can also take a quick look at the spectrum diagram of this particular thing. So actually I'm going to disconnect it over here, and I'm going to move over my camera and see if we can get it high enough to the spectrum generator, which is now investigating the signal. So I see some pulses there, but that suggests that I'm not looking at the right frequency range right now. So let me go and change that signal to 1 megahertz, which I just did. Okay, now we see on the spectrum generator what we expect to find, I think. Let's use a marker to see what we got here. Marker number 1. And what do we see? We see a main fundamental at 1 megahertz. We see one coming in at 4, one coming in at 5, and okay, let's use again the marker for this one here. And then at 10, 11 and 12 harmonics. Now let's look back at our Excel sheet, and that's exactly what we see here. We create the 4th and 5th and the 10, 11 and 12 harmonics. So that looks quite like you would expect it to be. There is some spurious elements here. I mean, they're not terribly strong. It's quite some decades of dBs lower. But then again, we're on 14 bits resolution. So that is to be expected, that we do see some unwanted spectrum components here. But altogether, I think this really works well. I mean, we're able to generate a waveform. We're able to load it into the device without too much trouble. And we actually can see on the spectrum analyzer what the signal looks like. Now, turning now to the Siglent, we're also going to try to get a waveform imported into the device. So, just to save time, I've already prepared the device to pick up one of these waveforms that were coming every 5 seconds out of my my chirp generator. Yeah, there we got one. We got a waveform here. We can stop it for a moment. And we're going to try to see to get that into the arbitrary waveform generator. So AWG, it's already at arbitrary, that's fine. ARP types, and actually now we get to see the various presets that we got here. And so where we have to go apparently is here to channel. That will be the channel copy part. And we get file does not exist. And this is the problem. I've not found any way in which how to do this. I've tried a variety of different things here. I went to the acquisition menu. I tried to use the sequence acquisition mode. So we would have 2 acquisitions going on. Let's start it. Let's wait, and we need to wait again 5 seconds. Let's wait for 2 acquisitions, so both segments are being acquired, so taking us 10 seconds in total. And after that, there it should come. Yeah, so now both segments basically are fine here. Let's go back to the waveform generator. File does not exist. I've tried to save files basically to the internal memory in all the different formats. I've tried anything I can think of. I never managed to get it going. I also posted this on the EEV post, but I did not get any reply by people that managed to get it going. So for the time being, my conclusion is that it doesn't work at all. But I think it's a bit worrying. I mean, this device has been on the market for over 2 years now. There could have been firmware updates if there was really an issue or so. So I'm not very satisfied here. For me, loading a waveform into the arbitrary waveform generator from an analog channel, that's the reason why you want it in a scope, but it's not happening. Of course, you could try to get that scope channel exported somewhere and try to re-import it again with a USB stick, but then you will have to do a number of steps in between, because you cannot do more than 16 megapoints, and you need to do a number of other edits. So it will be very, very intensive type of steps that you need to take. But probably with that workaround you might get something going. Now, trying the other route, which is the memory stick, and actually I'm gonna show that right now. So then we would use the USB option here. We can select the memory stick here, and here I have the file that already prepared earlier that you saw from the Excel sheet. So this is only 16 kilopoint. That's the maximum memory size that we got here available. So I'll be selecting it. This is the load button. To me, it looks like a save button, but well, might be my thing. But I've always been afraid to overwrite files, but in Siglent's language, this is a load button here. Import wave file success. So the wave should be there. Sorry, I have to get up for a second. Disconnect. Connect it to the waveform generator. And actually get a signal going. Yeah, sorry, I now have my acquisition stuff all different than the way I wanted it to be. So I'm going out of this sequence mode again. I'm going to auto mode. And let me see if we can pick up the signal. Is the device off? Ah, yeah, there we go, there we go. We're fine. And there we got the waveform that was prepared from the computer. I can show it. I can also show it on the spectrum analyzer, but I can tell you it's pretty much the same signal as we've been before. So I'll save you the time for that. So this works. Still, something needs to be said. Unlike Roden and Schwartz, Siglent provides no documentation at all when it comes to the format of this comma-separated file. Its manual is completely silent on it. Eventually, with a bit of reverse engineering and finding a file somewhere on the internet that was actually meant for another Siglent device, I got it working. Similarly, there is not one single piece of software or so that is mentioned on the Siglent website that is compatible with the SDS2000x Plus series. It's already 2 years on the market, but no software there available. I've been trying to work with the EasyWave software that is mentioned in the manual, but not on the website as a compatible program. So I spent quite a bit of time trying to work into EasyWave. I am able to transfer something from the scope to EasyWave, but the other way around, EasyWave recognized the oscilloscope. I can see the oscilloscope number coming in properly. It asks me in which of 1 out of 4 slots I want to save something. I hear some relay switching and that's it. The file is not in the oscilloscope at all. I tried numerous things. It doesn't seem to be working at all. Also, other people, I've not read of people that managed to get things working with this device. The more recent version of that program, which is called EasyWave X, seems to be completely incompatible with this oscilloscope. So in terms of software support, but also the whole working of analog channels and the arbitrary waveform generator, yeah, I can only conclude that the Siglent SDS is very disappointing. It simply doesn't work. Of the 3 oscilloscopes, the Roden and Schwartz is the only one where you can find here a set of 4 output pins on the front panel, which reflect its pattern generator it has on board. And I'm quickly gonna review that pattern generator right now. So to get to it, you go to the app screen where you got a number of apps, you go to the app generator and you get to see exactly the pattern generator file here. So what can the pattern generator basically do? It allows you to create a number of different types of patterns. So square wave, that is pretty straightforward. A counter, where the little icon here already shows what to expect for the counter. Upwards, downwards, frequency, etc. I'm going to skip that for a moment. We got manual here, where we can just set particular lines, manual, high or low. We got a number of serial protocols, which I'm not going to talk about right now. I'll do that later when I talk about training symbols. And what I find the most interesting part here is the arbitrary pattern generator. And so what we got here basically is a device that can create a series of states out of the 4 ports in a predefined way. Now this predefined way can be set up in the device itself, and that happens via pattern setup, or it can be loaded from a file and it can be saved from whatever pattern you have generated. So let's first take a quick look how we will be able to do it ourselves. You go to the pattern setup and it's rather simple. You get to see the 4 output lines. The total pattern length actually can be up to 2048 values here. I'm just going to put 8 values now, and wherever you are you can create values by entering them here via a screen. But perhaps even more the easier way to do is to use the draw function and to just draw those areas where you would like a 1. And I'm not sitting straight before the screen, so it's kind of hard for me now to control the device. But you can basically draw out your own pattern as you wish to do. Now, this is perfectly fine for small patterns, of course, and rather handy. But for larger patterns, you might want to create them elsewhere if you got more complex type of patterns. So for that, basically, you could load them from a file. That particular file is described in the manual of the device. And it actually contains a command line, so you could also just send over the same command line to the device and it would also do the same thing if you do it via a USB or a network interface. But now we're going to do that with that file. And to make things a little bit easier, a while ago already I wrote a little program. It's an Excel file that allows you to draw your own file basically, and that creates the command file that you save in a text document and can load into this in this device. So I'm quickly going to show you now one that I prepared myself, and also this little program I'll leave in the comments of the video, so we can load a particular pattern. My pattern now is on the front USB. It's called pattern SCP, and SCP basically is like for a command file. You would load it and it will be loaded. It does go out of the screen. I don't find that super convenient, but of course we can go back here. We can go to pattern setup and we got exactly the pattern here that we also have created in that file. It's a fairly long one, but if we look here at this particular place, we can also recognize that in the Excel sheet. So after you prepared your pattern, either manually or you uploaded it by a file, you can go to the timing setup menu and there you can choose the bit time or the period. Of course they are inverse to each other, and if you do not want a continuous pattern that keeps running forever, you can go into the bust mode, and in the bust mode you can basically choose how often a particular pattern will be repeated and the idle time that you have selected to be between the bus. And there's also a possibility basically to trigger it using a button on the device. So and I think that happens over here. Here it repeats itself forever. Here we go to 1 time, and every time we press this particular button here, that would trigger the particular pattern to be outputted from the front panel. So I think that's most that I can say about this, but this particular way of creating a pattern and doing some testing can be very convenient. People working with microcontrollers and all types of things. Often we work with serial protocols, but sometimes you just work with value series, etc. And having a pattern generator can be a rather useful type of tool of trade, which is offered by the RTB. Coming to the end of today's episode, I want to quickly look at the training signals that these devices can generate, because they can be particularly useful in order to solve particular situation, but also get yourself a little bit more acquainted with how the systems work. So such training signals are offered by the RTB and by the Keysight DSOX. The Siglent does not provide any training signals at all. So let's first look at the RTB then. It's got no analog training signals, but it got a couple of digital type of signals, and it got a number of protocols. And also by virtue of it having 4 pins that we just saw in the pattern generator, it can not only create CAN and LIN type of signals, but also type of protocols that require multiple lines, like I2C, or serial protocols or SPI protocols, and so that can be very useful. It's actually the only device I have here that has this type of test capabilities. Of course you can also build it with an Arduino or anything else you would like to do. I'm not going to demonstrate all of these. We've already seen a couple of them during the protocol decode. But I would like quickly to look at the digital signals, the pulse width type of things. So that type of things on the RTB can be looked at here on the track, and we see here that for these two different modes, they're interactive. He's calculating different values, and yeah, we get to a stable condition. And here we see that the pulse width within a particular signal is being calculated, and via math function is being plotted on the screen. So this gives a little bit of an indication, I think, of the different training type of signals that the Roden-Schwarz device can offer. Now, also the Keysight DSOX has a number of different training signals, and it's particularly strong in the analog domain, where we got a set of 14 different types of training signals. But on the digital side, it can also create some burst, and it can do a couple of protocols, but it's limited to one-line protocols, and in this case that's CAN and LIN. But let's take a closer look at the analog training signal. I think it's worth looking at, and it's good to note that the training signals always come out of the demo output, so it's not coming out of the signal generator output, but the demo output here, and they can be accessed via the help function training signals. Then we can activate them, and then actually you see that particular output, which was before used for probe compensation, now outputs the training signals. So here we got a whole list of different options. We have a sine with noise, we have AM stuff, FM, repetitive things, glitches, and all type of things. And the interesting thing is that if we select something and we press a couple of seconds here, we always get like a help screen with information about that particular thing. And this shows really the level of detail that you find in this Keysight device. It's all very, very well thought out. I mean, it doesn't offer everything, but the things that are there are done with a lot of attention for details. And looking into these training signals, is also worth to pick out one of them that allows us an opportunity to further explore the oscilloscopes that we got here, and that is the ones that have glitches here. So we'll turn now to the clock with the infrequent glitches. Demonstrating one of the training signals of the DSOX instrument also allows us to test a little bit the performance of the three instruments that we're looking at. So what I would like to do now is activate one of these training signals. They're here, training signals, and I'm gonna select the clock with the infrequent glitch, and I'm going to activate its output. We're seeing it on all the three devices now. So what are we looking at now? We're looking at the 50 kilohertz clock signal, but it has an infrequent glitch in there. Actually, there's one glitch per 50,000 clock cycles. So basically that's about 1 per second or so. So by having this clock with this infrequent glitch signal here, we can test the ability of these devices here to show issues with clock signals or otherwise in current behavior of a device under a test. And being able to observe these type of things relates to a specification that we will see for all the devices in the specification sheet, the waveform update rate. And here on the screen you see the waveform update rate as published for the devices, where we see that the SDS actually has the highest published waveform update rate. Then it will be the Roden-Schwarz, and then the Keysight itself. But a few things we have to look a little bit more carefully at when we look at these specifications. These specifications often stress the best possible waveform update rate. However, that is often achieved only when the device is in a segmented memory mode or a sequence mode, where it's recording the waveforms but is not outputting these waveforms to the screen. Now, since I want to look at these clock signals on the screen, we'll actually not be using that mode, so we actually have to look at other maximum as the specifications specify them. Also, in this regard, it's perhaps important that while the other devices talk of a waveform update rate, the Siglent talks sometimes about a waveform update rate and sometimes about what they call the waveform capture rate. But this is seemingly used interchangeable in the specification. It's kind of in the same sentence for the value, so I must assume they mean the same thing by it. Now, so looking at the signal now, we see the 50 kilohertz signal. I put all the devices to the same time base and comparable vertical types of setting. It's all 10 microseconds per division. And we also want to choose the optimum setting for each of the devices to be able to see that we're doing. Now that is often related to the acquisition system setting. So here for the Roden and Schwartz, basically I'll choose the shortest record length. That's probably going to show me the best results here. And in terms of what I've just been talking about, the fast segmentation mode, I'm going to turn that off. So we get the maximum screen updates here. On the SDS device, should be able to go here, acquire menu. I'll also be choosing the shortest one here. When it comes to the sequence mode, that's a little bit more puzzling to me how exactly that's defined, but I've tried all the different settings and now I've chosen the setting which gave me the best results in terms of seeing this on the screen. And the Keysight does not have particular settings in this respect. It is always on its default settings. Now, also to be able to see this signal in the best possible way, you might already see that we see some glitches coming by on the devices, but they're rather short. We have a high update rate, and I'm not sure whether you're actually going to see all of this on the screen of my camera. So what I'm also going to do is use persistence mode, and to activate the persistence mode on the RTB device, we'll go to display, persistence, manual persistence, and then from the menu we can select different options, and I'm going to choose half a second here. Why half a second? I know my glitch is there about every second or so, if every glitch were being picked up. So by half a second I have persistence, but still will be able to see individual glitches here. Now to the SDS, let's also choose the best settings. We'll go to display, we got a persistence mode. Here we don't have that many choices. We cannot do half a second. I'll choose a full second, which might have two glitches coming close after each other, right after each other, might be show only as one single glitch. But later we see this is not really going to be an issue here. And on the SDS device, I will go to display, persistence, I'll go to variable persistence and also choose half a second here. So we're good. So now let's go and look at what we see here. And starting here with the Keysight, yeah, it's very clear. I hope you can see that. We're getting a lot of glitches to be seen. Let me see if my intensity is already on maximum. No, let's move it a little bit up. Maybe you get to see it a little bit better. That's kind of a funny way to show the intensity levels. And here we quite frequently see the problems in this clock signal, even if they occur only 1 out of 50,000 clock waveforms here, cycles. Also on the RTB, if we look now, and this is a bit of a lottery, so we never know exactly how we're going to see. We need larger time frames to do some statistics on it, but we regularly will see here problems with the clock signal coming in here. And then if we look at the SDS, that's a bit of the problem. We hardly get to see anything. So even though this device has the best specification on paper when it would come to being able to observe this type of glitches, only rarely they are to be seen. And I did some longer time checks on it. I did several checks of full minute periods and counted manually the number of things, and I'm showing the results right now on the screen. And that suggests that the Keysight and the Roden and Schwartz are kind of similar in their ability to see this type of glitches, but the SDS is hardly able to observe any of such problems in the signal. I'm playing around with the other parameters that might affect it. I think it's at the optimal setting now, but if anybody believes there should be different settings, that let me know in the chat. But my preliminary conclusion is that this is a device that is not well capable of picking up infrequent signals here. I did a bit more testing also with masking, and actually I come to very similar results there, but I'm going to keep that for a later episode now. So the conclusions, and those who have watched today's episode in its entirety will already know what I'm going to say, and those that are just jumping to the conclusions will learn about it right now. So let's look at the free oscilloscope when it comes to signal generating capabilities. First, the function generator on the RTB is very good. Everything works as it should, has modulation, has burst, has sweeps, everything that you can desire, and I think it's a quite capable replacement of a standalone device if you don't have one. In many of the use cases it might suffice, although there are of course cases where a separate one will be desired. The SDS works but is extremely basic, can just basically play a waveform but no modulation, nothing else really we can use. On the Keysight DSOX the function generator is also quite good. When it comes to arbitrary signals, the RTB I think is very good. Everything works as expected, and also since you can already do on the device itself taking away from a channel and also doing the cutting and preparation, I think it's very satisfying. On the Siglent SDS it's to a significant part non-functional. You cannot get one from a channel. The working together with the Siglent software has many problems in it. And since this device is already on the market for some years now, there have already been quite a number of firmware upgrades. I'm not too sure whether this is going to be fixed on any short terms or so. And the DSOX does not have an arbitrary waveform generator. When it comes to pattern generator, the one on the RTB is very good. There's of course not that much reference material because there are not so many pattern generators that have that type of shape there, but I think it's a useful functionality, not available on the Siglent or the Keysight. And finally, when it comes to training signals, the RTB I think is very good, and particularly when it comes to protocols, because it can do 4-pin protocol training signals. The Keysight DSOX I think it's very good, particularly in the analog domain. So we got a wide choice of analog waveforms with kind of distortions and glitch in it that are very useful, and the SDS does not support any training signals. So I think the conclusion for today's episode is fairly easy. The RTB, the Roden and Schwarz RTB, is by far the best device when it comes to generating signals, and second place would be for the Keysight DSOX. Thanks for watching this episode, and keep tuned for the next episode coming. And if you got any feedback, including feedback on today's episode, perhaps managing to get things working that I didn't get working, etc., do let me know. See you next time.